Hi there and welcome back to the Hurdy Radical Synthesizer. And in the last video we did a kind of a re-evaluation, refocus on it because I hadn't done anything for a while on it. And I actually went through all the old videos and watched them and took the view that we'd gone round in circles a bit. And I guess there were circles we needed to go around and did some interesting stuff on the way. But we came up with a simple architecture for the sound generation of our radical synthesizer. We need some kind of resonator, and then we see some kind of a system to drive the resonator to keep it sounding, which I've called an encycler, which is just does that, drives the resonator. We're not modelling any physical system. And then we've got a sounder on the end which shapes the sound out of the resonator, which we're not going to look at today, and we're not going to look at the encycler today, I don't think. We're going to look at the resonator, and we just want to move forward and make something that works, and then we can, well, make it better. So I decided the resonator is going to be a delay line type resonator, which is like a string on a guitar or a violin, the nearest physical thing to it. So let us start by having a look at delay lines in digital systems quickly. Okay, a delay line. It's very simple in concept. You just have a lot of memory locations like this, and every sample you put a value in at that end, shuffle all the others down and take one out at that end. So there is a delay time of n over the sample rate. Okay. And how do we make that into a resonator? It has lots of uses, but we want to make it into a resonator. Well, we have our signal going in here and add some feedback. Sorry, the drawing's a bit scabby. Which is less than 1, because obviously if it was bigger than 1 it would just explode and overload. So okay, let us put, say we just put one impulse into here, like that. So that will go all the way down here, come here, come back here and go back into the start of the delay line. So we have that kind of thing. So there we have a repeated waveform which will have a spectrum. If there's a short pulse, quite a broad spectrum, and the frequency of this waveform will be, that is T. So it's repeated every T, so frequency equals simply 1 over T. So there we go, we have a resonator, and a resonator that will support quite a complex spectrum, whereas our mass on a spring resonator was simply supported the one frequency, which doesn't make for a very exciting synthesizer. So there we are. We have our resonator. Okay, so just a word on implementing our delay line. What we in fact have is a long delay line, and within that we have a write point and a read point. Every sample we write a value to the write point, and then the next we move that pointer on and write to the next point, and similarly the read point tracks behind it, and this is our T. So that enables us, we just need to write one sample and read one sample, whereas our original way of doing it, we were shuffling all these samples down, which is very wasteful of processor time, just copying between one memory location and the other. Also, since this T time gives us our frequency might be anything. It's not necessarily going to correspond to a whole number, T being a whole number of samples. So what we are in fact doing, so instead of our read point being that sample or that sample, it might be here in the middle. Okay, so our read point is between S1 and S2. So our read point is, say, at sample 31.223, and if our write point is at, say, 50, the write 50, I know the write point is always a at a sample point. Then our delay time is T equals 18.77 samples, and say we're using a 48 kilohertz sample rate, which I am generally. The frequency will be 48,000 divided by that. The frequency will be 2,557 hertz, 0.2, yeah. So yes, there we go, we can make any frequency we want, and obviously we've got two values here, but we want this one in the middle. We say that's nearer S1 than S2, so our output equals 1 minus 0.23, because we're 0.23 of a sample away from S1 plus 0.23 S2. So that's how we calculate outputs from intermediate samples, and that's just interpolation. And if you look again at the mean green videos, I go into doing this at some details because we're actually reading from wavetables, which is a very similar process. Okay, so let us implement all this and see what we get. Okay, so here we are. This is our impulse. It's basically one cycle of a cosine wave. If you're familiar with a pulsar, that's all the pulsar uses for its pulses. And we feed it through our delay with a bit of feedback. We put it in, we just feed it in once and let the delay line run with the feedback, and we get this. There you go. Pretty boring, I know, but we're just getting our delay line up and running for now. We can improve it later, and that's the spectrum, and there it is as a spectral analysis. Okay, as I say, not very exciting. And I've also taken the same delay line and just fed a swept sine wave onto the input. And we get this. Okay, yeah, and you can hear the the resonances of the harmonics. So we're on the right track. So now we need to get our encycler doing something. So let's have a look at that. Okay, so how to drive our delay line. Now I started looking at our bow model and realised that our encycler actually has two different kind of modes. So a string and our simple mass on a spring. What we're actually doing with the encycler here is giving it a kick every time it comes round to keep it going, because it's naturally damped, or we add damping. And the kick it gives it balances out the damping, and you get a constant amplitude. Whereas if we look at our recorder type model, and I am still struggling to try not to model physical or electronic systems, but if we look at our recorder type model and we look at the picture, we can see the air is either actually going into the tube or away from the tube, and it flips from one state to the other, and the pressure waves coming down and back the tube are what cause it to flip. So we have a flip engine, again like our good old neon, which is high impedance, so the capacitor charges up to a certain voltage, then it flips to low impedance and the capacitor discharges down to a low voltage and it flips back to high impedance, and so on. And we tried to get our flip engine working, and without any success. So time for another go at getting a working flip engine. Okay, so instead of trying to think about neons or anything, or recorders, I've gone to probably the simplest system I can think of, or way of drawing it, which is a Schmidt trigger. Have I drawn that correctly? Well, is what it is. With an inverter. So that's in and that is out. So we start at with the in right at 0, the out is at its whatever it goes up to. Let's draw our two, these are our two levels, and the out, as we come up, we raise the V in. When we get to the upper threshold, the output will fall to 0 and will continue at 0. And if we now reduce the input voltage, the output will stay 0 till we get to the lower threshold, in which case the output will go high again. So now let's draw a resistor and a capacitor, and this is not really electronics, this is just to try and get our head around the behaviour of the system. So here we have time, and VC starts at 0, so VO starts at what I've called VS. This is VS. That's VO. So we have our two thresholds values here. So VC will charge up till it gets to our top threshold, then VO will go to 0, and VC will discharge till it gets to our bottom threshold. VO will go positive. So we will get it's kind of a ramp wave-ish thingy. So let's try and make one of those in software. Okay, so here it is. We've been through this at the start of these videos. Basically, if it's greater than a voltage, flip the output. Very crude, very simple, and as we saw the first time we tried it, not very effective. And here it is. We'll have a look at the waveform, which is as we expect, like a capacitor charging and then discharging. We can see here these sharp transitions from one direction to the other tell me that this is not going to work very well. So shall we just play it? And I have swept the frequency using the time constant of the resistor capacitor, modelled resistor capacitor, and that should be a continuously descending tone, and you can hear it sort of stepping. So all is not well with what we have here. And if we look at the spectrum, oh yes, we can see we're getting all sorts of stuff up to whatever frequency. So, not good. So, when we originally tried it out, we know for a start, digital systems do not like sharp transitions of the output here, like that. So instead of this, should we try and make it so that if the voltage is going up, when it gets to the trigger point, instead of going straight down, it goes down in a curve, in a controlled manner. So what we're going to say is high here, and then we are going to, whatever the input does, go in, the output is going into that curve till it gets to the end, and then it's in low mode and it can go back and do whatever. And this is just half a cosine wave. You'd imagine drawing a cosine wave. So it's just this half. So let us have a look and see how that does. Right, so I won't trouble you with the code, but this is the result. And if we were to look at one cycle, yes, you can see the peaks are now curving over gently rather than changing direction sharply. So that's looking good from that point of view, but what does it sound like? Oh dear, we still have that stepping, but if we look at the spectral view, we've got a lot less of the high frequency crud. So it's an improvement, but we really need to get rid of that stepping problem. Okay, so let's say we have our input to our Schmidt trigger arrangement is going like that, and our trigger level is like that. But let's say our samples are actually there, 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 and there. So it will start to trigger here, even if our trigger is as we just drew a nice, friendly, digital friendly curve, it will always start to trigger at a sample. So every cycle will be every cycle of our waveform will be a whole number of samples long. So that's what the stepping is. It's going from, say, 20 samples to 21 samples. We need to be able to trigger at a point between samples. How do we do that? Well, we know that this sample was below our trigger level and this sample was above our trigger level. So we can assume, because we don't have any choice, that the waveform was a straight line between them. So if we know this value and this value and this value, we can calculate that time as a fractional sample. So in the picture that's a half. So say our waveform's doing this, instead of going from 0 and then 1 on our half cosine wave, that is actually, say t equals 0.5 approximately is in this picture. The first sample here, this curve will actually start here. So our first sample will be 0.5 of a sample into the curve. Now the curve is half a cosine wave, so the curve is given by cos pi times, call this number n over the L. L is the number of samples that our cosine is. And then we scale the half cycle of a cosine out. But anyway, we don't need to worry about that for now. But this is all just floating point arithmetic, so n can be 0.5 in our example, 1.5, 2.5, 3.5, etc. So now our little curve between the two states is actually aligned to anywhere within this sample that this threshold was actually passed. Okay, here it is. Shall we play it? Brilliant, no stepping, no nasty noises. There we go, nice smooth waveforms, and okay, no, not too much high frequency stuff. I think we can live with that. So now we have a working flip engine. Let us see if we can connect that to our delay line and actually make a pitched sound. Okay, so as I tell myself, always try the simplest possibility first, see where that gets us and see what complications we want to do next. So what I've done is I've got our flip engine and I just put the output from it into our delay, and the output of the delay goes out and is fed back also to the input of the flip engine. So what we expect to happen here is the output of the delay starts at 0, so the output of the flip engine starts high. Okay, so after the delay time, the output of the delay will go high. I've just shown it a bit lower, so the flip engine will go low. So after another T del, the output will go low, so the output of the flip engine will go high. So we are simply expecting to get a square wave of a period of twice the delay time, which probably isn't going to be very musically useful, but we will see what happens. Okay, and this is the result, and it's doing what I expected it to do. What I'm doing is I'm increasing the drive level throughout the file and the frequency, or decreasing the delay time anyway, which has the same effect. So we can see here it doesn't make a sound till the drive level gets up to the thresholds, and it will actually flip. So let's see what it sounds like, shall we? Nothing here. Well, it sounds like a square wave, which if we zoom in is pretty much what it is. And you can say that one side is the input of the delay and the other side is the output, and we can see they are slightly out of phase. Well, they are, as we would expect, about 180 out of phase, degrees out of phase, anti-phase. Call it what you will. And if we look at the spectral view, yeah, not bad. I mean, we are getting sounds all the way up, but can't hear it doing anything nasty, and we're still getting, you can just see slight steps as it goes between whole samples. Don't know whether that's the delay line or the flip engine, but I can't hear them, so we are going to press on for now. So next I am going to try two things. I am going to try and make the flip engine feel a little more responsive to the drive level. Quite how I'm going to do that, I don't know. And I am going to add some feedback which goes back into the delay to make it ring a bit, because that's what happens in an instrument, so we can at least see what it does. So I shall do some coding and give you an update. Okay, so here we are with the feedback set to 10%. Let's play this one. And what's going on there? It starts at a lower frequency and then just jumps up as it gets Louder. Most odd. Okay, should we try the... what have I got here? I've got the next one, 20% feedback. Here we go again. And we get 3 different frequencies. We have here a 50% feedback, and we can kind of see there there's something weird happening. Okay, getting stranger and stranger. Shall we try the last one I did, which was 80% feedback? Oh, and you can already see there's some fun stuff going on here. Etc. Not what we were looking for. Okay, well, I had high hopes for that, and it seems to be, well, I guess a bit of a fail. I think I may know how I can rescue it, but I may actually now do some work off camera and try and get some kind of a working sound engine that we can turn into the start of an instrument. Of course, I fancy I've put rather a lot of videos out of it not quite doing what I wanted and what I hoped, and I guess they're not the most exciting videos on YouTube either, and I just need to sit and think rather than trying to explain my thought processes while I'm doing it. So I might do that in the background while I'm working on other videos and come back to you and say, hey, look at this, isn't it wonderful, hopefully. And I have at least one other video I want to do on the player interface, which I will do, which is just electronics and mechanics and stuff. So that should be more predictable. We should easier get a good result out of that. But for this video, again, as I say, I'm afraid a bit of a fail. So I shall just... so it goes, that's life. And on that philosophical note, I will take my leave for now. Goodbye.